Hi, everybody. Welcome back. In the last video lecture, we introduced the idea of the chemical master equation, and we went through the foundations of it theoretically, and ended up with this final result of a differential equation that describes how the probability distributions of finding different numbers of molecules of different species varies over time, and a way of writing down that based on the rules for the rate laws of each of those chemical reactions. In this video, we are going to start from that foundation and develop the tools to actually simulate system according to these stochastic chemical reaction dynamics. So let's begin by switching over to the slides. All right. This is the chemical master equation that we discussed in the last video. It's a differential equation for the rate of change of the probability distributions. And just as the mass action kinetic differential equations had left-hand side rates of change of concentrations, and they were expressed in terms of the concentrations, the chemical master equation has the rates of change of the probabilities of different numbers on the left-hand side, and on the right-hand side has the probabilities of different numbers of molecules, as well as the rate laws which depend on those. And so there's no real analytical path out of this for very, very simple systems like a single reaction. Perhaps there are ways that we can get an analytical solution, but for the general case, we can't. We require our numerical method to solve the problem instead. However, this sort of differential equation is fundamentally more complicated than those of mass action kinetics. In mass action kinetics, our differential equations were derivatives of really a number that vary with respect to time, a set of numbers. Or one number for each equation, simply the concentrations. And the Forward-Euler algorithm and related approaches give us a path for integrating that kind of differential equation. Here, our variables are actually probability distributions, they're curves. How we so Forward-Euler and those related approaches simply don't apply to this particular class of problem. Maybe there's ways that they could be extended, but it seems like it might be rather difficult. Instead, we are going to introduce an algorithm known as Gillespie's algorithm, or sometimes referred to as the Gillespie algorithm. And what it is it's a numerical approach that will be able to generate an individual trajectory, an individual time series of numbers of molecules through the chemical space, so the numbers of molecules over time. And it will generate them in such a way that they're fully consistent with the underlying chemical master equation. They're fully consistent with the probabilities. What this means is that if we did this, repeated this algorithm over and over and over and over again, and we analyzed the results, we would get the appropriate probability distributions. We can think of this also as what this is it's a simulation of one experiment, as if we were looking at measuring in one particular experiment, counting the molecules. Gillespie's algorithm gives us a representation of that. And of course, because these are stochastic systems driven by random chance, if we did the experiment again, we would get different numbers. We would get a different set of numbers. If we run the algorithm again, we'll get a different set of numbers in the same way. It's based on the idea that we can generate a sequence of reactions through time. And then from that sequence of reactions, we can convert that into a time series of the numbers of molecules. And we're going to be computing two things in each step. When the reaction occurs and which reaction occurs. All right. One of the foundations of the methods that we're going to use is this concept that the chemical master equation is a Markov process. And what this means is the transition probabilities don't depend on how we got to the state. They only depend on what the state is. Right? The reaction rates, the probability of a reaction only depends on where we are right now, and therefore everything that we learn from a Poisson process is directly transferable. Why is this? Well, if we think about how things are happening at a particular point in time, right? We can pretend that the system we're dealing with for each reaction, imagine that each reaction had a constant reaction rate, that the reaction rates didn't change with respect to time. In that case, every individual reaction is just a Poisson process, a very simple sort of system. Right? In that context, we would obviously be able to use the rules of the Poisson process to figure out the time to next reaction, and so on. If we have a Markov process, it doesn't matter whether we got to the current state by always having exactly the same rates, or we got to that state by a more involved process. All that matters is what are the transition probabilities at that particular point. Right? So the transition probabilities are reaction rates with our adjusted units. Our time between reactions is exponentially distributed with a parameter related to the rates, and so on. All right. Let's start off by defining the transitions. How are we going to compute the transition probabilities, the reaction probabilities, or reaction rates? This is essential. We need to have a rule for these probabilities for every individual reaction. These are going to be derived very, very similarly to the way we define the reaction rates for mass action kinetics, just with slightly different notation, slightly different unit scheme. So for an example, in a unimolecular reaction with some substrate molecule and some turning into some product molecule. So XS is one molecule, XP is another molecule. J simply indicates that what we're dealing with here are the reaction J. The transition probability of this, if it's a unimolecular reaction, well, the reaction rate is proportional to the concentration, proportional to the number of molecules. So it's simply rate constant multiplied by the number of substrate molecules. This is exactly analogous to the idea that the rate for a in the mass action kinetic model, that is the rate of change of each of these two species, would be some constant times the concentration of substrate, an exactly analogous expression here, just using numbers of molecules instead of the concentrations. The change vector that we discussed in the last lecture that we used to keep track of how numbers of molecules change for this unimolecular reaction has a +1 for the product, a -1 for the reactant, and everything else is 0. Right? We do have to be careful to think carefully about what the reaction is, what is really changing, and thus needs to go be addressed in our change vector, and what is participates in the reaction but does not change its form, in which case it might be involved in the rate law, or the probability rule, but not in the rate of change. We can compare a unimolecular reaction that converts, where a substrate gets converted into a product, with an enzyme catalyzed reaction that converts a substrate into a product. The change vector will be identical because substrate turns into product, but the rate law is different. And so what I have here is a Michaelis-Menten expression for the rate law. Again, the transition probabilities, the probabilities are computed with exactly the same kind of rule as for mass action kinetics. Michaelis-Menten, a constant, rate constant, enzyme concentration times substrate concentration over a Michaelis constant plus the substrate concentration. We simply replace all those concentrations with numbers of molecules instead of concentrations, and everything is exactly the same. We also need to be a little bit careful about things that can happen in our biomolecular simulations, where we're not really keeping track of everything. In biomolecular simulations, there may be some reactions that don't consume a reactant, and there may be some reactions that don't actually produce a product. It's not that there isn't a very low level of product or a consumed reactant in these cases, but rather that we're not explicitly modeling these. So for example, degradation of a protein in our model doesn't have an explicit product because we're not keeping track of the concentrations of individual amino acids. That is, we might write our model as a protein just disappears, goes into nothing. Here, the transition probability might be written as linearly proportional to the concentration, just like our ODE mass action kinetic inspired models had a linear degradation term. But the change vector only has a single -1 in it for the vector that's getting changed, or the species that's getting degraded, and everything else is zeros. We only have something on the left-hand side, if you will. Similarly, templated synthesis of RNA from a DNA template, synthesis of protein from an RNA template. These don't consume reactants within our model. They actually do consume reactants, individual amino acids and individual nucleotides, but we're not keeping track of those. And because we're not keeping track of those, the change vector for templated synthesis just has a +1 for whatever is being made and doesn't have anything decreasing, zeros everywhere else. And once again, the transition probabilities, the rate probabilities, the reaction probabilities are given by a form that looks just like we would use for the mass action kinetic inspired models. In this example here, we have a Hill equation where the amount of some, say, transcription factor Q is responsible for the transcription of species R. And I've just as an example used a Hill coefficient of 4 in this model. Right? The important point is this looks just like the types of regulated synthesis rates that we saw in our earlier models, just once again counting the numbers of molecules instead of in concentrations. Right? Once we have a rule for what all of the reactions are, the reaction probabilities, we can compute their individual transition probabilities, their individual rates. I now want to introduce an idea of the combined reaction rate. And this is going to be an important part of the puzzle. All of the reactions in our system are independent in a probabilistic sense. What that means is that if you think about, there's two different possible reactions that could happen, the probability of one and the probability of the other, they don't affect one another, right? They each have an independent probability. What this means is that if we want to ask the question, what's the probability that something happens? The probability that some reaction happens. We're not concerned about what reaction it is. We're just really comparing something versus nothing. Well, if everything is independent, the total probability of, and they're independent, they're also sort of exclusive in a infinitesimal sense, that if we think about in a very, 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 very small amount of time, only one thing can happen, right? And so if only one thing can happen, then the probability that something happens is simply the sum of the probabilities of each of those individual reactions. That is, I'm going to call this P0, P0 of X. P0 of X is the probability that at T plus delta T, X is no longer the same value that it was at xt, right? That is, the state has changed. Something has happened. A reaction has occurred. How do we get this? We get this by adding up the probability of each individual reaction. So we sum over all of the reactions and we ask, what's the probability that that particular reaction happened? We can write this as the probability that X became xt plus nj at dt. There should be a d, not a delta there. Given that we started at t, and when we add up all of those specific outcomes of ending up at a particular nj, the aggregate of that, the sum of that, is the probability that we are simply not at x anymore. We also know that each of these individual probabilities, the individual reaction probabilities, are given by our rate rule multiplied by dt. So this combined reaction rate is a sum over all reactions of the individual rate rule. And we're going to call that sum, ignoring the dt, just summing up the individual rates, let's call that alpha naught. And when we do that, we have that the probability that something happens is given by this combined probability alpha naught multiplied by dt. Now, why is this help? Well, the probability that something happens is given by alpha naught dt. The probability that nothing happens is then 1 minus that. That's the probability that we stayed in one place. This dual possibility looks just like a Poisson process. If we think about the Poisson process of counting just reactions of any form, we're not going to worry about what type it is. We're just going to say, did a reaction occur? Let's count that. Did a reaction occur? Let's count that. That's exactly what the Poisson process represents, right? It's a counting process where everything has to increase one by one. We're just counting reaction, reaction. We're counting the number of reactions. This looks very much like a Poisson process, but alpha naught isn't constant. In a Poisson process, alpha naught would be constant. But as we discussed earlier, these processes are Markovian, which means at this particular point in time, if we think about a very specific point in time and what's going to happen next, there's no difference between a Poisson process that had alpha not as being constant and this process where it's variable. In particular, the distribution of times between the reactions. How long do we have to wait for something to happen? It should follow an exponential distribution with the parameter alpha naught. Right? That is, the time we wait is drawn from an exponential distribution, alpha naught, where alpha naught is this sum. This is our first really key important piece. It tells us how long we have to wait for a reaction to happen. Right? The Gillespie algorithm, the first thing that we compute is the time we wait for something to happen. Right? A reaction just happened. How long do we have to wait for the next one? We do this, we add up all of the individual rate rules, and then find a random number that comes from a probability exponential distribution of that. Now, you might ask, how do we do that? How do we actually find a random number from a particular distribution? And it turns out this is actually a fairly easy thing to do in MATLAB or in almost any type of computer programming language. We discussed this exact problem in the Poisson equation, in this Poisson process lecture. We compute a random number from a uniform distribution, and then we transform that using the natural log. And so we sort of think about expanding that Poisson process rule to a Gillespie algorithm rule. I'm going to start off by defining some array to hold the reaction rates. And then we have to go through, and we have to, for every one of the reaction rates, we have to fill in the rate rule. And I'm leaving this sort of unspecified because for a general problem, I don't know what those are right yet now, right? But for a particular problem we're interested in, we will have a well-defined set of rules for those. And we just write them in. Write what those rules are. They will depend on the numbers of molecules in the system. After doing that, we add them all up. You can actually do this just by adding them up directly. There's an easy way to do this in MATLAB using the function sum. So sum reaction rates will add up all of the entries in here and give us an alpha naught. Again, there's more than one way to do this. Once we have our combined reaction rate, we're all set. We have everything we need to compute the time to reaction. We draw a number from a uniform distribution between 0 and 1, and then we transform that by taking the natural log of that, negative, and dividing by the alpha naught that we calculated. And that is the time we wait. How long did we wait till the next reaction? Once we have the time we wait to the reaction, we now have to figure out which reaction happened, right? How are we going to do that? Well, we've discussed the probability that a specific reaction occurs between t and some t plus dt is given simply by the transition probability, the reaction probability, alpha times dt. And again, that should be a D, not a delta. I apologize. Now, let's now think about a slightly different probability, right? Because we've already said, what have we just decided? We've already figured out the time to a reaction. That means we know something happened. How would we do that? What's the probability that a specific reaction happens between T and dt when we know that some reaction happened? We know that something happened. This is now the probability that say a specific reaction occurs, the probability that X changed to X plus Nj at some T delta T, knowing that we started at X at T, and that we're not in the same state anymore, that something happened. How do we find this? Well, we can do a little manipulation using Bayes' theorem. And Bayes' theorem lets us change the order of a conditional probability. The probability of y given x is the probability of x given y times the marginal probability of y divided by the marginal probability of x. And let's just sort of fill this in, calling with y being that a specific reaction happened. X went to x plus nj, and x being that something happened. So y is the probability of a specific reaction happening, And X is that some reaction happened. Right? So what we want is the probability that a specific reaction happened given that some reaction happened. And we're going to rearrange this to be the probability that something happened times the probability that a specific reaction happened divided by the probability that a specific reaction happened. Let me slow down. Px is then the probability that anything happened, right? The marginal probability that anything happened, alpha naught times dt, what we've just discussed earlier. The probability that a specific reaction happens. Right? This we've also said, this is the transition rate for that specific reaction times dt. Py given x is the problem we're trying to find. What's the probability that a reaction happened given that something happened? Well, and what would this first piece, what would this last piece, px given y? Px given y is the probability that some reaction happened given that a specific reaction happened. And this has to be 1. If we know that a specific reaction happened, we definitely know that something happened. Right? And this is where the simplification is going to come in. This first term is a 1. The second term is just the transition probability for the specific reaction. And the denominator is the combined reaction probability. The 1 disappears, the dt's cancel out, and we're left with a probability that's just a ratio of the rate of a specific reaction to the combined rate. So once we know a reaction has happened, the specific reaction has a probability that's just given by a ratio of what's the rate of that probability of that reaction to the probability of any reaction, or the rate of that reaction to the combined rate. How do we sample from this? How do we actually use a random number to figure out what reaction? Well, let's focus on noticing that we have the denominator is a sum over all of the numerators, right? So essentially the denominator is just added up all of the individual rates, and the numerator is each of those individual rates. We can also think about how would we sample from a subinterval of a uniform distribution. Let's say that we want to know what's the probability of getting a number between C and D when we know that we started off with numbers between A and B, and C and D are inside that range. Well, that probability is also just a ratio. It's how wide was that in between spot and compared to the full distribution. So maybe sort of can sketch this out. Let's say that we have a uniform distribution that goes from A to B. And what we want to know is what's the probability that we are inside a particular range that goes from C to D. Well, the probability that the number is inside this range is just whatever this width is, D minus C, divided by the width of the whole range, B minus A. A ratio of two numbers, just like the ratio of the numbers here. And so what we can think of is we can think of alpha naught as being this full range, B minus A, and these alpha j's being different little sub-ranges within this. And when we add up all of those sub-ranges, we get the full range. And this is going to be the key to how we choose the reaction. Let's think about this. We are going to essentially define a big range going from from 0 at one end up to alpha naught at the other end, right? We add up all of the reactions and get our aggregate or combined reaction rate. And each individual subinterval here is a particular reaction rate for the first reaction, the second reaction, and so on. And then what we're asking, what we're essentially going to be doing, we're going to generate a number from our uniform distribution from 0 to alpha naught. So we're going to generate a random number somewhere in here and then ask which range are we in. So if our random number, if our y was here, then the first reaction happens. If the y we generated was here, then the third reaction happens. If the y we generated was over here, then the last reaction happens. Right? Very simple. We're going to choose from a uniform distribution between, sorry, and I should have actually, it looks like there's some missing letters here, between 0 and alpha naught. And then we ask, if y is in the appropriate interval, that's which reaction we choose. How do we do this in MATLAB code? Well, compute the reaction rates in the same way, sum them up in the same way. Now what do? We generate a random number between 0 and 1. Simply multiplying that number by alpha naught will change that into a random number between 0 and alpha naught. And then we just need to ask this y mod, where is it in the sequence? Where is it in, which subinterval is it in? And one way we can do that, there's more than one, is to just do a loop where we loop over each reaction, starting at the first, and we ask, are we in that section? And so we ask, are we in that first? Are we less than that first little piece? And if we are, then we set the reaction to that and break. And if we're not, we go on to the next. I'm using a sum over a progressively larger piece because what I'm actually asking in this code is we're going to first of all check, are we in the first interval? Yes or no? If yes, then we keep that. If not, are we in the second interval? If so, keep that. If not, then move to the third. And there's a fairly easy way to do this simply by asking, were we less than this value? If not, were we less than this value? If not, were we less than this value? And so on. And that's exactly what this kind of sum up to j minus 1 represents and what we have here. Right? Okay, so we've now discussed how we can calculate a time to reaction, how we can choose a specific reaction, how do we put it all together into Gillespie's algorithm? Well, we iterate over a certain number of steps, given some certain starting conditions, and at each step, what do? We compute each reaction rate and add them up. We compute the time to the next reaction, drawing from an exponential distribution using this combined rate. We select the next reaction to occur based on a subinterval of that combined rate, and then we change the numbers of molecules based on which reaction we chose and go on to the next step and repeat. The one last little piece of MATLAB we might want to discuss is how we do an number update. The best way to do this, or maybe not the best, but a well-defined way to do this is simply with a series of if and else if statements. We ask if our reaction was the first one, then update the numbers based on that reaction. If it was the second reaction, do a different update based on that reaction. If it was reaction 3, do a different update. And in this example, the first reaction creates A only. The second reaction degrades B only. And the third reaction converts A into B. Not a necessary part of the code, but what I've added in here is a last statement that if I don't get a 1, 2, or 3, and I only have 3 reactions, something has gone wrong, and so I give a little warning message. All right. All right. If we think about our code for a Poisson process, you can now imagine putting these other pieces in place within this general structure. We'll need to keep track of more than just one molecule. We'll need to expand to have more than one individual species we keep track of. We're going to have to, instead of using just alpha, we're going to want to use alpha naught, which means we have to add a computation of the rates in here before doing that, right? And after calculating our, instead of just having a simple update of one molecule, what we're going to expand this into is to choose reaction and then update the numbers. Right? But the basic structure will be the same, simply expanding on the Poisson process. All right. Now, in summary, we've discussed Gillespie's algorithm. We've introduced Gillespie's algorithm as this framework for simulating a molecular system with stochastic dynamics. It's derived very much based on what we learned from a Poisson process by taking advantage of this Markov property. We think of counting reactions just in an arbitrary sense, in a general sense, and that gives us the time to reaction. We then can use, once we know a reaction has happened, then we can get a very simple way to figure out which reaction happened. And this overall process is very easily simulated within MATLAB. There's a fair number of steps present, but MATLAB provides all of the tools necessary to do that, from generating random numbers, from the structure of looping over the number of steps, the selection of individual reaction, of which reaction using conditional statements, and so on. All right. So that actually wraps up the sort of this intellectual content part of these Module 2 lectures. There will be a couple additional tutorial videos on some of the details of MATLAB that might help you implement this to actually work on Gillespie's algorithm. And the second part of the MATLAB project for this module is, in fact, implementing using Gillespie's algorithm exactly the same system that in part A of the module project you implement in a mass action kinetic model. Until next time, everyone, please take care and be well.